Welcome back to Chapter 6. This section we're going to be looking at Section 4, which is on exponential growth and decay. Now, a lot of what we're going to do in this section doesn't really use calculus so much. A lot of it is actually just the same exponential growth and decay that we've been seeing since at least Algebra 2. The only part of calculus is kind of how those equations come to be. So as far as calculus goes, this one's an easier one, but the problems can still be difficult. So let's take a look. Our learning targets, we're going to use separation of variables to solve initial value problems. We've been doing that for the past couple sections, or so far this chapter. Solve differential equations of the form dy over dt equals ky, where k is a constant. That would be the rate of change is directly proportional to whatever the y value is. The rate of change of the population is directly proportional to the population. And that's where we're going to see that these exponential functions come from. But again, that's a rate of change of y is directly proportional to y. Solve applications involving continuous compounding of interest, solve applications involving exponential growth and decay, and find exponential functions whose graphs pass through 2 points. So, first thing we're going to look at is the whole separable differential equation thing. We've been doing this as we've been solving differential equations. Some of them can be solved, some of them cannot. In order to be solved, at least at our level, they need to be separable, which means you can put all the variables on, or you can put one of the variables on one side of the equal sign and the other variable on the other side. So our definition here, if it's written in the form 1 over f of y gy equals g of x dx. So all the y's are on one side, all the x's are on the other side. So looking at it, we can have a differential equation right here, dy over dx equals xy squared. And then y equals 1, x equals 1. This would be a solve for y. So we're going to find the general solution. The first thing we need to do, the very first thing we need to do in any of these problems, once again, is separate the variables. Right now, we can't do that. We first have to deal with that squared. So we get dy over dx equals x squared, y squared. Now we can divide, we can multiply to get 1 over y squared equals x squared dx. Once we have those variables separated, we can find the antiderivatives. So 1 over y squared, a lot of times we have 1 over something, people naturally like knee-jerk, natural log. Now, if we had 1 over y, it would be natural log. This, remember, is y to the negative 2, so we can add 1 to the exponent and then divide by the new exponent. So that'll be y to the negative 1, and then divide by negative 1, so that's negative y to the negative 1. So the derivative, we'd multiply by negative 1 to get positive y to the negative 2, which is what we have. Then equals 1/3 x cubed plus c. You have to have the plus c. That's where this comes in. So right now, we can actually substitute that stuff in before solving too much further. Or we could solve further and then substitute it in. It does not matter. The value that we get for c, depending on what steps we do, will change at the time, but once we get to the end, it'll be the same. It won't matter. So I'm going to substitute in, move it up here. We have negative 1 to negative 1 equals 1/3 times 1 plus c. So that's 1/3. We can subtract 1/3 to get negative 4/3 equals c. So we have negative 1 over y equals 1/3 x cubed minus 4/3. All right, well, we need to get to y. So the first thing, let's multiply by that -1 to get positive 1 over y equals -1/3 x cubed plus 4/3. Then we're going to need to flip these fractions. I'm going to rewrite the side with the x's using a common denominator. So this is -x cubed plus 4 over 3. And so now when we flip it, we get y equals 3 over -x cubed plus 4 minus x cubed. And so that would be solving this for y. Again, this is not something that is new. We've been doing this for a few sections now. Remember, the very first step, we separate our variables. Then we find the antiderivative of both sides. We make sure we include the plus c. When given those values, you plug it in, and then you just solve for y. So this is something like it will be on the AP test. So we need to know how to do that one. Laws of exponential change. So as I mentioned, we are going to start out with the rate of change is directly proportional to the thing that's changing, right? The rate of change of the population is directly proportional to the population. The rate of change of the savings account is directly proportional to the amount in the account. That's what gets us this type of equation. And so from here, we can solve this for y. So the first step, we would separate our variables. So we divide by y, so we have 1 over y dy equals k dx. So now we have 1 over y, that is natural log of y, equals k is just a constant, so it would give us a derivative of k, kx. Right, then how do we, plus c, how do we get rid of a natural log? We go e to the power, e to the power. So this gives us y equals e to the kx plus c. We can use some properties of exponents. When we add exponents, that means we're multiplying two things with the same base. So instead of e to the kx plus c, I'm going to switch the order. I'm going to go e to the c times e to the kx. Well, e is a number to a constant. What is a number to a constant? It's just another number. It's a constant. So this whole e to the c could just become c. Or yeah, we'll make it c. E to the kx. Now, if we wanted to plug in a point, like we don't have a point right here, but when x equals 0, y will equal y naught, which is the starting amount. Why would we call it that? Well, why not? No, the naught, the little 0 subscript just means the initial, the at times 0 type thing. So if we plug in 0 for x, we have e to the 0, which is 1, equals y naught. So this number in front, that c, is just the initial value. So we have the rate of change, that k is the same as it was in the initial one, but y equals the initial value times e to the kx. We've seen equations very similar to this in the past. And here's it's again the law of exponential change. So if y changes the rate proportional to the amount present, and y equals y naught when t equals 0, then we have that equation we just found. Constant's the exponential constant. If it's bigger than 0, it's growth. If it's less than 0, it's decay. So is it positive or negative? I know when we were first learning about it, we had y equals a times b to the x, and the b was always positive. If it was bigger than 1, it was growth. If it was less than 1, it was decay. That negative in the k value would make it a 1 over b. So it would make it 1 over e, which is a number that's less than 1. So that number less than 1 or a negative in the exponent is the same idea. And we'll talk about different bases in just a couple minutes. So what if we're looking about continuously compounded interest? We have a few different interest equations. We have the interest equation where it is compounded at any random time. So R would be the yearly rate. It's generally speaking over a year. N would be the number of times it's compounded over that year. So if it's compounded quarterly, that means it's compounded 4 times over the year. So we'd make N equal 4, and then T would be the number of years. It doesn't have to be years. You could do days, and it's compounded hourly, so N would be 24, and T would be in days. But generally speaking, with the applications we see, this is in years. So the differential equation for something like this, it's the amount that we're looking at. So the rate of change of the amount equals the rate times the amount, and the initial condition at time 0 it equals P. That would stand for the principal, because this is generally amount. So we could find this equation. We have dA over dt equals RA. So we would separate our variables. 1 over A dA equals R dt. And this is going to be exactly the same as the last one. It's just the letters are different. Natural log of A equals RT plus C. We can go e to both sides, which will give us A equals C e to the RT. But when we plug in 0 for t, e to the 0 is 1, so that initial thing is the principal. So we have A equals PE to the RT. We've seen and used this equation many times in the past. So we'll keep using it. So let's suppose we have an $800 in an account that pays 6.3% annual interest. How much will we have 8 years later if the interest is compounded continuously or compounded quarterly? So we just plug it into the equation. So compounded continuously, that's this one. Because it's the area under that curve. So it doesn't matter, like it's the n is infinite. So we can go A equals 800. E to the pays 6.3%, so that's 0.063 times t. We're looking at 8 years later. And then we just crunch those numbers. So I'd start out with the exponent. 100e 0.063 times 8 is about 0.504. Well, it is 0.504. And then e to that power. And just like every time before, I'm using whatever numbers are in the calculator, not, well, 5.504 was that. But like this number is going to be 0.655 something. I'm not going to retype it. I'm just going to use what's there. Or 1.655 blah, blah, blah. So that times 800 gives us 13, 24, 26. Now, for the end, I am going to leave it at the 2 digits because we're talking about money. That 26349, that 349 doesn't matter. 26 cents. So we have $1,324.26 in the account after 8 years if it's compounded continuously. What about if it's compounded quarterly? Well, A of 8 would equal, our principal was 800 times 1 plus 0.063 over 4, because quarterly means it happens 4 times a year. And then to the 4 times 8, so how many times are we actually compounding this thing? And so 1.063 divided by 4 is 0.01 something plus 1 is going to be 1.01 1.01575 to the 4 times 8 is 32. So we'll take that to the 32 times 800 is 1319.07. That's a 1. So if it's compounded quarterly, we have $1,319.07 at the end of 8 years. The continuous compounding will always get you more. It will rise faster. If we compounded yearly, we'd have less. So that is using those interests. Notice as we were doing the problem in both of those parts, there's no calculus involved. The only calculus we did was over here when we were looking at like figuring out what that equation is that we already knew. Radioactivity and half-life. So radioactivity, and the problems are basically the same. The difference is it's the half-life. And what half-life is that is the time it takes for there to be 1/2 of something. And it's always compounded continuously. Nope. A equals PE to the RT. Let's fix that there. A equals PE to the RT. So it's always compounded continuously because the radioactive isotopes and stuff don't really use calendars and mark out hours or anything. They just do what they do. So what a half-life is that means that it doesn't matter how much we start with. At the end of the half-life, we're going to have 1/2 of that value. So if we were solving for this, we would divide by P, which gives us 1/2 equals e to the RT. And then to solve for the time, because the half-life is the time, we would take the natural log of both sides. So you have natural log of 1/2 equals the natural log of e to the RT, which is just RT. And so solving for time, we would just divide by the rate. Or a lot of times we'll have the half-life is a certain number of years. So we have the time, we have to figure out what R equals. So either way, I mean, solving for either of these variables is going to be the same. But we'd have R equals natural log of 1/2 divided by T. You can remember this, or you can actually go through those solving steps. I generally go through the solving steps, not showing every single one of those steps. But when I'm doing a problem like this, I'm just like, all right, well, I know that 1/2 equals e to the RT, so natural log, and divide. But our definition of half-life, so here they solve for t because the half-life is t is natural log of 1/2 over that rate, which they just use the variable k instead of r. But then the problems are done the same way as any continuously compounded problem is. So using other bases, we do not have to use base e. We can use whichever base we want. Sometimes it makes more sense to use a different base. For instance, and so the equation's the same. It's y equals y naught times the base to the a rate times t. Now the rate might not be the rate that we're thinking of, but that's what it is. So we could be looking at a hornet problem. At the beginning of the summer, the population of a hive of bald-faced hornets, which are actually wasps, is growing at a rate proportional to the population. From a population of 10 on May 1st, the number of hornets grows to 50 in 30 days. If the growth of the population continues to follow the same model, how many days after May 1st will the population reach, oh, it was May in the beginning too, will the population reach 100? So, we can use the same deal. So we have y equals, let's see, we want 100 equals the initial amount was 10, and then we know it was growing. It went from 10 to 50, so it increased by 5, like a factor of 5, like we multiply by 5, but it didn't do that in a day. It did that in 30 days. So if we want each day, we're going to go 1 over 30 times t, which would be the number of days. And then we can just solve for this. We divide by 10. So we get 10 equals 5 times t over 30. Then take the log of both sides. I do natural log just because that always works. So this will be a t over 30 times natural log of 5. Because the exponent comes out, we can divide by that natural log. Now, you cannot cancel those. Remember, the natural log 10 divide by natural log 5. You've got to do natural log 10 and then divide by natural log 5. Equals t over 30, so let's multiply by 30. So t equals 30 times natural log 10 over natural log 5. At that point, that's a calculator deal. So natural log 10 is about 2.3 divided by natural log 5 ends up about 1.43, then times 30 is 42.92 days. So how many days after will the population reach 100? During that 42nd day. So 42, or in this case 43, will probably work as well. So that's when it would reach that amount, which if we think about it multiplied by 5 in 30 days, so it would multiply by 5 again for the next 30 days. So 50 times 5 is going to be too much, so it should be in between that 30 and 60. So that looks good. Carbon dating. Oh, and notice, like, nowhere in this problem was calculus used. There were no derivatives, there were no integrals, there were no limits. This could have been done at an Algebra 2 level. In fact, we did problems like this a couple years ago in Algebra 2. Same thing with this one. Scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. So the first thing we need to do is we need to find that K, or that R, that constant. So remember, we had just on that last slide, RT equaled natural log of 1/2. Well, if we divide by T, because we know it, it was 5,700 years, we can find R. So natural log of 0.5 divided by 5700 is like negative 1.21 times e to the negative 4. So r is going to be small, negative 0.0001216. But remember, I'm going to use whatever's in the calculator there. So now we can set up our problem. Find the age of a sample in which 10% of the radioactive nuclei have decayed. So if we start out at 100% for our principal, we're going to have 10% left. Or you could start out at 0.1, and 1 would be your principal. Does not matter. E to the RT, and I'm just writing R instead of writing out that long decimal. So we can divide to get 0.1 equals e to the RT. We can take the natural log of both sides. And then we can divide by R, because we know R. So we're going to have, the time is going to be the natural log of 0.1, which is about negative 2.3, divide by that R, which is still stored, and we get 18,934.99. Which I would say it's 18,935 years old. So, again, that problem was something that we've done for the past few years. There's nothing new on this entire slide. Newton's law of cooling. We had some problems like this as well. Now, Newton's law of cooling, the rate of change of the temperature equals negative K times T minus Ts. The Ts is the surrounding temperature. So what happens here is that if I set my coffee cup down on my desk in my office, which is right now about 58 degrees, it's slowly going to cool. It's not going to keep going until it freezes. It's going to gradually become the same temperature as the room. Well, that used to be the case. My girlfriend just recently got me for Christmas a very fancy coffee cup that's actually heating up my coffee, and it stays the same temperature until it's done. But, for normal humans, your coffee cup is going to slowly cool down until it reaches the surrounding temperature. And it's really not going to change the surrounding temperature much. Like, my coffee cup is not going to heat up my room as it's cooling. The room's going to stay about the same temperature, and the cup changes. And so that's directly proportional to the temperature, and the differential of the temperature specifically. So the bigger the change in temperature, the cooler or the quicker it's going to cool. And then at the end, it's going to slow down. So I love this as dt over dt. The capital T and the lowercase t do mean different things. The capital T is temperature, the lowercase t is time. And as I mentioned, the T here, it's not so much the temperature, it's going to be the temperature minus the surrounding temperature. It's that differential of temperature. So we can move the stuff, do the solving, and we get that T minus Ts is going to equal the initial temperature minus Ts times e to the negative kt. When we solve, we end up with two different deals. We factor it out to get the T naught minus Ts. You can go through those steps if you like, but this is the equation for Newton's law of cooling, which also works, by the way, if you were heating stuff up. It's the same idea. If you put an ice cube on the table, it's going to warm up in roughly the same way. So how do we do a problem like this? Well, a hard-boiled egg at 98 degrees Celsius is put in a pan under running 18 degrees Celsius water to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take for the egg to reach 20 degrees? So we're going to use the initial point that we're given at 5 minutes. It's 38 degrees Celsius. So our temperature minus surrounding temperature, let's get the equation. So the temperature minus the surrounding temperature is 18 degrees. That's the water. Is going to equal the initial temperature minus the surrounding temperature. 98 minus 18, e to the negative k times lowercase t. So first, now we'd plug in our point. So t equals 5, temperature is 38. So we have 38 minus 18 equals 98 minus 18. This is just going to be 80. E to the negative k times 5. And so our rate is going to be in minutes because that's what we're using. We don't need to convert it to hours. It's going to be degrees Celsius per minute. So 38 minus 18 is 20 equals 80 times e to the negative 5k. Divide by 80. 20 divided by 80 is 1/4 equals e to the negative 5k. We can find a natural log of both sides. And then divide by negative 5. So k is going to equal natural log of 1/4 over negative 5, which is 0.27725 something. So I'm just going to say k equals 0.277, knowing that I'm not actually going to use that. I'm going to use the more exact number in the calculator. So we can plug that into our equation. T minus 18 equals 80, because that's 98 minus 18 anyway. E to the negative 0.277 t. So how much longer will it take the egg to reach 20 degrees? So we plug that in for there. The other question it could have asked is how long, or what will the temperature be after a certain time? We'd plug in for t. So 20 minus 18 is 2. We can divide by 80. E to the negative 2.77 t. 2 over 80 is 1/40. We're going to do natural log of both sides. And divide by that negative 2.77. So t will equal natural log of 1/40 over negative 2.77. Natural log of 1/40 is negative 3 point something. Divide by the negative 2.77 gives us 13.3. So minutes. So after 13.3 minutes, the egg should be at about 20 degrees Celsius. So that's Newton's law of cooling. Again, notice that there was no calculus involved in this. Like the exponential stuff, like the problems, don't really require a lot of calculus. So you have that to look forward to. Anyway, I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.